All right, welcome to today's lesson on sketching parabola. Now, last week we looked at solving parabola, and if you remember, the idea behind that was not so much solving it, but actually calculating the x-intercepts. So this week we're going to look at sketching them and what that means and looks like and how it works. So on your screen you should see a Desmos page with a graph attached to it, and I've got a collection of green points. Now those green points are in the shape of a parabola, and they join up. If you join them up, they look like this, which is a pretty poor sketch right there. But you can see it's a nice U shape, and that shape is called a parabola. All right, so let's have a closer look at what's going on here. On the left-hand side, you'll see a table of values. So here's the input, x, and these are all the different inputs that I'm using. And then the output is I'm squaring whatever the x input is. All right, so minus 4 gets put in, 16 pops out. Minus 1 gets put in, 1 pops out. A half gets put in, a quarter pops out, and so on. Now what you might notice is that when I put in 1, 1 pops out, because 1 times 1 is just 1. 1 times 1 equals 1, or 1 squared equals 1. All right, so you can see that the point is the same. Up here, you'll have 2, 4, because 2 squared equals 4. Now what you might also notice is that directly opposite 2, 4 is another point, and that point is minus 2, 4, because minus 2 times itself equals positive 4 also. So a parabola exhibits some symmetry. The points should always be directly opposite each other. So 2, 4 and minus 2, 4. 1, 1 and minus 1, 1. These 2 points are the same, or the same outputs, different inputs but the same outputs. And these 2 points will have different inputs but the same outputs. So this symmetry is shown by drawing a line down the middle, and it's this line that we call the axis of symmetry. It is the mirror image on each side. So if I take all these points and flip them over there, I should get the exact same curve on the left-hand side, or vice versa. All right, so the axis of symmetry is a vertical line down the center of a parabola. All right, so I'm just going to erase all this stuff now so we can have a look at a few other things. All right, so moving back to some of our points, you might notice that when a half goes in, a half times a half is a quarter. When a quarter goes in, a quarter times a quarter is a 16th. You might notice that Desmos has actually rounded this. It's 0.063 here, but over in the table of values, it's 0.0625. All right, so don't be fooled by what you see there. All right. So basic parabola is this one here, which is x squared. Other things to note about it is that it sits firmly at 0, 0, because 0 squared is 0. 0 times 0 is 0, which you can also see in the table of values on the left-hand side. All right, so point of interest here is this lowest point. Notice that on each side of the lowest point, so going to the right and to the left, it goes up the same way. So this lowest point here is a point of interest. All right, so it's a point of interest. So if you're ever asked to sketch a parabola, you will need to put in this lowest point, or it could also be the highest point, and the parabola could open downwards like this. All right, it's actually called the turning point, where the parabola changes direction. All right, so if you ever get asked to sketch a parabola, you will need to show this turning point, where the parabola changes direction. Okay, it could be a low or a high. So we've talked about the axis of symmetry, we've talked about the turning point. Another name for the turning point is also the vertex, because vertex means corner, and this is where it changes direction or does what a corner would do. All right, so this parabola, and it just keeps going on to infinity, is called y equals x squared. That's just it. Whatever the input is, the output is squared. Okay, now we're going to look at a few other forms of basic parabolas and see what happens when I move them around. So you might see this box here. I'm going to do this one. All right. So here is the red one, which is a collection of points where the input is the same, but the output has had 3 subtracted from it after it's been squared. So you might notice the input, the green one says the output is 16, but the red one says the output is 13, which is 3 less than 16. Minus 2, regular output is 4, other output is 1, and so on down the tree. So all the way up to 16, and the output is 13. So what that does is, as you can see from the red dots, is it's moved the entire parabola down by 3 units, like this. So you can see that this green dot here at the top has been moved down 3 units. This green dot here has been moved down 3 units. This green dot here has been moved down, and so on for all of them. All right, so you can see that each dot has been moved down by 3 units. That's why we say that this change here shows a vertical translation, which is a vertical change. So if that change had said +3, you would see the dots being moved upwards by 3 units. If it said +10, they would be moved up 10 units. If it said down 500, they would have been moved down 500 units. All right, so this -3 here on the end shows vertical translation, as you can see there. So we'll just move on from that now. So back to the picture here, we come to the next one. Which is the black one. Now, the black one is a little bit harder to see because of the points that have been used, but I'll do my best to show you. So the black one you can see is a parabola looking like this. I've run out of points on the right-hand arm, but you can see that it would continue going up like so. All right. Now, if you're looking at the table of values, you can see that there's a brackets there, and it's got a -2. Now this -2 happens before the squaring happens, which means that the -2 affects the x value. So before anything happens, we take the input, we subtract 2, then we square it. So this input here of -4 gets 2 subtracted from it. So -4, take away 2, which becomes -6, and then squared. And -6 squared is +36. So you can see where the input was originally 16, it's now 36, which is a huge change. This input of -2, originally it was 4, now it's 16. All right, this input here of -2, subtract 2, then square, becomes -4 squared, which is 16. All right, and same for -1, -1 minus 2, squared becomes -3 squared, which is 9. The way I like to explain it is that the input of -2, because it's had 2 subtracted from it, is now acting like the input that was 2 away from it. So where its original answer was 4, its new answer is the same as one that was 2 away from it, so 16. 1, where its original answer was 1, its new answer is 9, which would have been the answer that we would have seen it for -3 in here. All right, and the same for all of them. 4 produces an answer of 4 because it's subtraction. All right, 2 produces an answer of 0 because it's subtraction, so 2 minus 2 squared, that becomes 0 squared, and that becomes 0. So what you might notice there is that the turning point, this bottom point here, has actually jumped 2 units across. Okay, so this change that we see in here, where the one on the right hand side, this change after the squaring produces up-down movement, this change in here that happens before the squaring produces left-right movement. All right, to show you that again, the green parabola is mapped here. and the black one is the one that has the change, and you can see that it's moved left, right. So the way I would show you that is that this green dot has actually shifted to where that black dot is. You've seen the turning point move already. This dot has shifted across to there, this dot has shifted across to there, and so on. All the dots have shifted sideways. So this shows horizontal translation. All right, now these ideas in this lesson, vertical translation, horizontal translation, are all really important ideas that we need to get our heads around early because we'll be using them for the rest of the year. So take the time this lesson to make sure you understand up, down, left, right, how the changes make the shift happen. So the up, down happens after the squaring, the left, right happens before the squaring. You might want to write that into your books. All right, now I'm going to show you one more change that can happen, and then I will tie it all together in one form. All right, so bear with me. All right, so in this next bit, I'm going to show you what we call dilation. And I'm just going to, yep, there it is. All right, so I've got now a purple set of dots. And you might notice that those dots are a little bit more stretched, you could say, than the green dots. So here are the green dots, and if we join them up to make a parabola, we can have it looking like this. All right, if I join the purple dots up, it will look like this, roughly. You notice that my parabolae are not great. All right, now, to zoom in a bit further, oops, I'll do it this way. Still not right. There we go. Nope. There we go. All right, you get the idea. So let's have a look here. We can see that in the table of values, we have a 2 out the front of the x squared. What that does, it multiplies. So where these two changes were added or subtracted, -2, -3, this change is multiplied. What that does is it drags the points away from or towards one of the x or y axes. All right, so this one pushes the points away from or towards the x-axis, and so is called from the x-axis. Okay, so this is dilation from x-axis. Okay, there is dilation from y, but we won't talk about that this lesson. So this is vertical dilation because it happens from the x-axis. It means it's going up or down, which is away from or towards. So I like to call it vertical dilation. Okay, so just like we had vertical change and horizontal change, we can have vertical dilation and horizontal dilation. All right, now to visualize it, you can see that this green point here has actually been dragged vertically upwards to that green point there. All right, you can see that this purple point, this point has been dragged up, this point's been dragged up. You will be able to see, if I zoom back out a bit, that, and I'll just get rid of the parabolae lines, and I'll draw all the blue ones back on. You'll be able to see the dragging happening between each of the points. There, that's better. All right, so this one's been dragged up, that one's up, this one's been dragged up, this one's been dragged up, this one's up, this one's up. These ones you can't really see the change, but you can get the idea from the vertical blue lines. All right, so each point gets dragged away from the x-axis. And if we go and look at the table of values, so original value for -4, input -4, output 16, is double. Where it was 16, it is now 2 times 16, which is 32. So it's being dragged away from where it was by a factor of 2. All right, now you know that multiplication is repeated addition. So this change, dilation, is a fast change. Where horizontal and vertical translation are slow changes, so a movement of 3 here is only 3 units on the graph, this change here is quick. So this is doubling, means the purple graph is a lot more stretched. All right, so you can see the change reflected where -1 was the input, normally 1 the output, now it's doubled. Where 2 was the input, 4 was the output, now it's doubled. All right, and what this change does, if I can show you, is it makes parabolae tall and thin, or short and fat. All right, so this purple one here, compared to the original, which is the green one, you can see that it's a lot taller and thinner. All right, so a number in there, a whole number in there, bigger than 1, produces tall, thin parabolae. Okay, if I go and change that number to a fraction, all right, and what I'll do is I'll edit the other graph so that we can keep the purple one in there. I'll edit this one to be x, and I'll put a 1/2. There we go. All right. So you can see now that this black graph, if I draw them all on, the black graph looks like this, the purple graph looks like that, and the green graph is in the middle. So this fraction produces fat, wide parabolae. All right. So this dilation factor produces narrow or broad graphs, whereas the translation moves it from side to side or up and down. All right, so there's a few things to remember. The terminology you need to remember is that this bottom point here is called the turning point or the vertex. The axis of symmetry is across the line across which the parabolae are reflected from left to right, and vice versa. All right, we have dilation, we have horizontal translation, and we have vertical translation. Dilation stretches graphs, translation moves graphs. All right, so the stretch, if you notice I didn't point this out actually, the note, if you notice down here on all 3 of these ones which have dilation, the turning point is in the same position each time, right there. And if you look at the table of values, you can see why 0 times anything is still 0. So even though there's a dilation factor in these 2, it's still times 0. All right, so that's a stretch. It proves the stretch. Now, to tie it all together, we've got one way to write all of the forms, and that is this way here. We can go minus h squared plus k. So you might want to write this in your books. A, this is the dilation factor. This is multiplied to the front of the brackets. K, this is the vertical translation. And H, this is the horizontal translation. And remember that it's H for horizontal. Now you might notice that it's a minus H in there, whereas when we looked at it in the graphs, it moved it to the right, being a minus number, and the left to the negative number. This is counterintuitive. Just remember that it's the opposite change to what you see written in the equation. Later on in the year, we'll go into the why of that and look in more detail at it. All right, so to look at a few examples, we can see this in action. So you might see a question that says, here is a parabola, and we want to sketch it. All right, so luckily that's one of the ones that we actually did in our introduction. So you see it's the regular one, but it's been shifted down 3 units. So you just count 0, 1, 2, 3. There's my new vertex, and you draw your nice arms like that, and you label it y equals x squared minus 3. Notice that on mine I also put arrows on each of the arms to show that the graph keeps going. This is a very important point, and not just me being pedantic, so make sure you do as well. You might find a question that says something like this: y equals 2x minus 1 squared plus 3. So this actually has a combination of changes in it. We just read them out one by one. So we see it's been moved up 3. So we go 0, 1, 2, 3. It's been moved to the right 1, opposite of that. So it's been moved this way. So there's my turning point. It has a dilation factor of 2, which makes it tall and narrow. So it's going to look like this. Now, there's no way without a proper scale and all sorts of information for us to, or for me to be too pedantic about how it looks. It needs to have a nice curve, and it needs to be noticeably taller and narrower than a regular parabola. All right, so you would label that as the equation, and you would label the point of interest, which was the turning point. 1, 3. Notice it's been moved up 3, cross 1, which is these numbers here, so that's the turning point. Okay, if you want to try and find the x-intercepts, you can, but don't stress. And then lastly is a question that might look like this: y equals minus x plus 1 squared plus 4. And we haven't talked about a minus sign hanging around at the front, and I'll quickly explain what it does. It just flips everything upside down. So earlier I alluded to the fact that a parabola could be turned over, and that's what does it, the minus sign out the front. So you would find your up translation, so it's been gone up 4, 1, 0, 1, 2, 3, 4. It's been shifted to the left 1, so across to there. So there's my new turning point, but it's a sad face, so it looks like this. Arrows on the arms, label it, and there is my parabola. All right, so it's pretty straightforward sketching parabola, but you do have a little bit of vocab and terms to keep track of in this lesson. So make notes in your book and then get on with the questions.